So now we are down to the final topic of this nuclear unit, nuclear power. We use technology, and technology requires energy. Now, in the old days when we wanted to plow a field, we could do it ourselves, or we could put a plow onto a large animal and have the animal walk through a field and have the plow cut furrows behind, and the animal would supply the energy. Then during the Industrial Revolution, we came up with more and more advanced technology, and we needed another power source in order to take care of all of that. And the steam engine was invented, batteries were invented, and eventually alternating current in the form of electricity was discovered and implemented and engineered. Well, there's many ways to get electricity to your home. One way is to burn coal, oil, or natural gas and use the heat to boil water, turn the water to steam. The steam turns a fan blade called a turbine, which is connected to a magnet that rotates inside a coil of wire. You see, it turns out that if you change a magnetic field inside of a coil of wire, it creates an electric field. And when you turn the magnet north, south, north, south, north, south, then what it does is it sets up an alternating sloshing of electrons back and forth through a wire, which we call electric current. In the United States, that electricity sloshes at the rate of 60 cycles per second. And your power adapters have to be very specifically geared for that because in Europe, it's 50 cycles per second. So we can burn fossil fuels, which we've done for a long time. But there are other options. We can create electricity directly by using solar power. We can also turn fan blades to turn a generator by having water run over the fan blades, as in hydroelectric power, or we can have wind do it in wind power. We could even have tidal power. It's pretty cool. But nuclear power is another interesting option. There are two ways that you can get energy out of nuclear reactions, one of which we're using right now. And the other one, there is currently a project underway in Europe to create the first power plant that operates off of this that could conceivably, in the next 10 years, lead to a major breakthrough in how we get our electricity. So let's have a look at them. First, where does this energy come from? Well, Albert Einstein discovered the relationship between mass and energy with his famous equation E equals mc squared. But it took Lise Meitner to discover how you could make use of this equation to extract large amounts of energy from nuclear reactions. Both of them have elements named after them, Einsteinium and Meitnerium. During a nuclear change, mass is destroyed. Now, wait a minute. I thought you said you couldn't create or destroy mass and convert it into a huge amount of energy. Wait a minute. I thought you said you couldn't create or destroy energy. Well, yeah, the laws of conservation apply to physical and chemical changes. But during nuclear changes, mass is destroyed and converted into energy. It turns out that mass is just super concentrated potential energy. Now, in nuclear decay, natural decay, the amount of mass is so incredibly tiny, you'd never miss it. But it still gives off enough energy to keep the core of the Earth liquid after billions of years. But these changes release far more energy than that. If we take E equals mc squared, m represents the mass that's destroyed by the nuclear change. It's called the mass defect, and it's measured in kilograms. And c squared is the speed of light squared, which is 9 times 10 to the 16th meters squared per second squared. And E is the energy formed by the mass defect in joules, which is a derived unit, kilogram meter square per second squared. So let's take a look at this particular form of extracting energy from the nucleus. We take a large nucleus, and there are not many nuclei that can do this. Uranium-235 is the only isotope of uranium that can do this. If you hit uranium-235 with a slow-moving neutron, this will split the uranium apart into two smaller nuclei. Now, you'll notice that the example in the equation and the example in the animation are not the same. There are many different ways the uranium can split. But on average, krypton and barium are produced. And three additional neutrons are released. And those neutrons absorb the energy of the reaction and move very, very fast. So we can have those neutrons passing through water. The water heats up. The water turns to steam. The steam turns fan blades in a turbine, which turn a generator. You get the idea. And those neutrons don't get used up. In fact, if you can figure out a way to slow those neutrons down, you can get them to be absorbed by more uranium-235 to create a sustained chain reaction that will keep this going for a long time. That's nuclear fission. So in a nuclear reactor, we have the following components. First, we need a high enough concentration of uranium-235 to keep the reaction going. Now, uranium-235 exists in far less than 1% of all samples of uranium. So we have to enrich the uranium by removing uranium atoms that are not 235 from the sample. Now, 3% is all you need for a nuclear reaction, between 3 and 5%. If you want a nuclear bomb, you're going to need to enrich it a whole lot higher than that, let's say 90%. And so the technology involved in making a nuclear reactor is much more accessible than the technology required to make a nuclear bomb. So this is what happens. A neutron will hit a uranium nucleus and split it apart. The splitting of the nucleus will produce additional neutrons that will split additional uraniums. The only thing is, you want to be able to slow the neutrons down as they move from one nucleus to another, and this animation does not show that. So how do you slow those neutrons down so they can be absorbed? Well, you use a moderator. A moderator is a substance that will slow neutrons down without being absorbed. In the United States, we use heavy water, where the water uses hydrogen with a mass of 2, deuterium. Deuterium oxide, or heavy water, is really good at slowing down neutrons without stopping them. You also need a way to stop the neutrons dead in their tracks if you want to control the rate of the reaction. You can see how this can get out of control really quickly. I mean, you tweet and then, you get a tweet, then you retweet it, then they retweet it, and then they retweet it, and pretty much it goes viral very quickly. It's exponential growth. But you don't want exponential growth unless you have a bomb. So you need to limit the number of neutrons that are flying around. And for that, we use what are called control rods. Control rods are made of a treated steel that can actually stop neutrons dead in their tracks without themselves becoming radioactive. And they control the rate of this fission reaction. The control rods move up and down in between the fuel rods, which are the black ones here. If you want the reaction to go faster, you raise the control rods. If you want to slow it down, you lower the control rods. And if you want to stop the nuclear reaction entirely, you just drop the control rods all the way down, because the water acts as the moderator. I'm going to start this over again. You can see the water absorbs the heat of this nuclear reaction, and this high pressure water is pumped into another chamber where it heats up lower pressure water, which turns into steam. The steam passes into a turbine, which spins a magnet inside a coil of wire 60 times per second in the US, 50 times per second in Europe. The steam is then condensed using water from an outside source, usually a river or a lake. The steam condenses back into water and is pumped back in to be turned back into steam again, giving you 3 loops, 2 of them closed, 1 of them open. No radioactivity will actually transfer between this first loop to any of the other loops. Isn't that loopy? In any other power plant, this reactor core would be replaced by a furnace, which would burn coal, oil, or natural gas. But that would also produce air pollution, and nuclear fission reactors do not produce air pollution. Surrounding them is a containment shell to prevent any accident from taking place. And a nuclear reactor is not capable of undergoing a nuclear explosion because there just simply is not enough uranium-235 to sustain that. However, these reactor cores can melt down, and when they do, they can put radioactivity into the surrounding environment, just not a nuclear explosion. The number of meltdowns is extremely small. There was Chernobyl, of course, there was 3 Mile Island, and there was Fukushima during a major earthquake in Japan. Other than that, nuclear reactors have operated without incident for decades. Now, we do get nuclear energy out of fission. We don't yet get energy out of fusion. And that's a shame because even though fission reactions can produce 1,000 times more energy than chemical reactions, fusion reactions generate 1,000 times more energy than that. Fusion is the ultimate source of energy if we can harness it, and we haven't yet figured it out. Two small nuclei will collide at high speeds, and they have to be high speeds because nuclei are positively charged. And if they're moving too slowly, they'll just repel each other. They have to be moving fast enough so that they overcome their natural repulsion and merge. And when they merge, mass is destroyed and converted into energy. Thousands of times more energy than nuclear fission. Now, this happens every second of every day in stars. Hydrogen in the centers of stars is crushed into helium and generates the heat that keeps the sun going. But on Earth, it's very difficult to reproduce the incredibly high temperatures and pressures that are needed to make this happen, which is why we don't have nuclear fusion reactions yet, at least not of the time of my recording this tutorial. Now, in the sun, we have two hydrogen nuclei combined to form helium plus energy. And this is the same reaction that scientists are hoping to exploit in the first nuclear reactor that will actually give more energy than it requires to operate. See, that's what's needed. If you're putting more energy into it than you get out of it, then what good is it? We want it to produce more energy than it takes, and we're working our way towards that right now with a research project. Now, it looks like the law of conservation of mass is obeyed. 2 plus 3 is 5. 4 plus 1 is 5. But remember, this change takes place at masses smaller than the ones place. We're talking the hundredths place or the tenths place, changes that won't show up when you just add up whole numbers. So these are the masses of the particles involved, and if you add those masses up, the mass of the reactants total is 5.12005 AMUs. And the mass of the products you can see is very slightly less. If you round it off to the nearest whole number, you'd never even notice the loss in mass. But that massive loss, which is called the mass defect, is very real. And it doesn't look like a lot. A tenth of an atomic mass unit? I mean, that's not a lot of energy. But remember, that's just the mass lost for each time this happens. In a nuclear reactor or the sun, this is going to be happening millions, billions, trillions of times every fraction of a second. So that mass does build up. And not only that, you're going to take that mass and multiply that mass by the speed of light squared, which is a very large number. So even though the amount of mass that's destroyed is tiny, you're multiplying it by a large enough number that you get a reasonable amount of energy out of it. You don't need to have a whole lot of fusion taking place in order for you to have a devastating amount of energy produced. So if we're going to convert 2 moles of hydrogen into 1 mole of helium, which would be to say 2 grams worth of hydrogen, well, let's see, actually it wouldn't be 2 grams, it would be 5 grams because the masses are 5. What we would do is we would just multiply it through, and that would give you actually I can math. That would be 20 billion, billion? Yeah, 20 billion kilojoules worth of energy. That is a tremendous amount of energy and will absolutely vaporize your house and beyond. So don't do it at home. Now, if we compare fusion to chemical change, let's say we're going to do the fusion of hydrogen into helium versus the combustion of hydrogen, the burning of hydrogen. The amount of heat released for fusion is 20 billion kilojoules. For the burning of hydrogen is only 242 kilojoules. So you can see that the amount of energy released during fusion is massively greater than during a chemical reaction. So if you have a choice of which one to use for a fuel, and by the way, this fuel right here, this is what's used to get rockets up into the air. All right. This could solve all of our energy issues because our source of hydrogen is water, and there's plenty of water. Hydrogen is the most common element in the universe. So the nuclear change, if we can make it happen, nuclear fusion will be the answer to all of our energy questions. And that is fission and fusion. And by the way, before I finish this on this blank screen, nuclear fission is currently being used to generate electricity, not just for homes, but also for nuclear submarines and aircraft carriers. And in addition to that, in countries that do not have much in the way of fossil fuel resources, they rely almost entirely on nuclear power, although some are now starting to use solar and wind in order to generate electricity as well. And that's all I have to say on the subject. So we are now finished with Unit 4. The next unit will be all about how electrons work. So until then, have a wonderful day, be well, and bye, 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 bye.